Hello, my name is Lena Behram. I'm welcoming you to our webinar about the new features in the upcoming release of the Medis Suite MR CT. The technical lead of applied research, Peter Kitzler, and the product manager, David Hautemann, will show you the deep learning algorithm for LV contours. The demonstration will take about 15 minutes. If you have any questions during the webinar, you can use the Q&A function, the option you can see on the top of your screen. So you can write down your question there, and then we are going to answer the question during the webinar, or we will send you later on an email with the answer. So yeah, let's start with the webinar.
Welcome, everybody. So my name is Peter Kitzler. I'm the technical lead of applied research at Medis, and I'll give a little bit background on the algorithm and some technical points regarding this new technology. And David Hautemann, the product manager of MR and CT at Medis, will later really do a live demonstration of how this is going to show up later in the product in practice. So I want to talk about a few things. I want to briefly discuss some of the deep learning background. What is it? Where is it coming from? Go into the contour detection algorithm that was developed at the Leiden University Medical Center that we have now are going to be integrating into the Medis software, and show how that goes into our outerCue pre-processing workflow, and we'll see then demonstrations of that later, how that really looks. So maybe a bit background on the deep learning. Actually, there are quite a few terms floating around also in the news: machine learning, artificial intelligence, and the deep learning. If you ask different people, you get different definitions, and some people are very strict and some are less strict in these definitions. But usually in practice, they actually refer to some neural network technology that was trained to perform a certain task. And that is basically what also we want to show today this technology is based on. And although you see a lot of recent news about this, and a lot of people are very enthusiastic about it, and there's quite some interest in there, it's actually pretty old technology in the basis. So the idea of having neural networks, so a set of independent neurons that are connected later in a network and can therefore communicate data to each other, is pretty old. This is a shot I took from a paper from 1965 where this sort of setup was introduced. And the basic idea is that you start with some input layer, so that this could be an image, like an MR image, and then you feed all those pixels to different intermediate layers, and they're all connected with each other. And each of these connections can have a different weight, so they have different influence on each other. And then you can go all the way down, make it smaller, and in the end you have an output layer, which could be the prediction of a certain type of what is this image, what is on this image visible, or and that whole concept is pretty old. And the way that actually this such a network learns is by what's called back propagation. So the idea is that you start with your images on the left, which are just your pictures. You run it through this network, which is actually initially just starts off randomly being connected and set up. And you get some answer from the network in this final output. And let's say initially the network says, I think this is an image of a dog, but actually it is a human face. So you need to know for this set of images at the start, you need to know exactly what is the real answer to your question. And basically what you then tell it, say, okay, you said dog, but it is a human, and you can sort of compute what is the error in this answer. So you have to basically rephrase it into a mathematical question. You can compute like a real error, and then you propagate this back. So you say, in order to make the dog look more like the answer of human, we have to adjust some of these weights in the network back, and you propagate that back. And if you repeat that for a very large number of images, then the network learns how to better predict. And in the end, you have a very good predictive network. Finally, and this is sort of the thing that we are now going to show later, and what we have is that if you have such a network, you can run an unknown data set or unknown image to it, and you get a prediction, and you're pretty confident that it's okay because you trained it on a large number of cases. And there's a lot of theory behind this as well, but basically you can approximate very complicated algorithms with such a network without actually much manual tweaking. There's no manual tweaking. The computer learns by just revisiting large number of data sets over and over again, and this way it learns. Also, this idea of looking at images and predicting something, specifically the convolutional neural networks, which is again a mathematical way where you actually slide over an image in sort of a window where you're looking at images and a patch of the image, and actually multiple patches can interact with each other, and there are things that get extracted at different levels. But again, not something that is super new. In 1998 already, a very good performance was reached on classifying numbers, handwritten numbers, with these convolutional networks. Although the performance at that time, the computation power was not sufficient to really make this work efficiently in practice. Then a real breakthrough came actually in 2012, and we're still in the sort of the aftermath of this breakthrough, where a lot of now new exciting things are being developed, where there was a challenge written out for visual recognition of images, so just classifying common pictures like holiday pictures that you have, was a yearly challenge where a lot of people participated in, and for years people were slowly getting better, but it was never big jumps until suddenly somebody dropped the error rate, which was about 28% at that time, to 16%. And that was a huge influence that had. And the method that was used by the team that won this challenge at that time was indeed neural network based, and it was actually trained on very large number of images. And the reason for this breakthrough they're twofold. One is really technology. So we have much more computing power, specifically the GPU, so the graphical processing unit. So actually the hardware that is used normally for running video games is very well suited for running these computations at full speed, making it feasible to run much more images through such networks. And there were some theoretical improvements as well, where people realized that certain theory behind these networks could have been improved by just applying different theoretical concepts. So you see here the graph where the performance of the error rate of this challenge dropped dramatically, and there's a nice trend with the blue line showing the number of entries where people were using GPUs. So suddenly everybody was doing this. So of course in academic this was picked up as well. So these are some pictures where within Nature the terms machine learning or deep learning, how often they were used, and you see really after 2012 sort of this hockey stick sort of exponential growth. And this is a slide from mid 2017, so I'm sure it's even bigger right now. And of course within the medical field, people also picked up on this. So this is from last year's RSNA, some quotes and some photos. So where you see like large group of people queuing up for a session on machine learning at the RSNA, people standing outside and queuing. And but a large part of what people also at that moment says is that we need something to make this new technology really available to the end user in the clinic. And I think that's what we want to show today, that we have something that was very nicely developed in an academic sense, but moving it to really to the practical domain. So this is the paper that just came out the 9th of October by the group at the LUMC. So Chen Tao, the first author, and Rob van der Geest is a senior author, where Medis as a tight collaboration with. And they did a very thorough multi-vendor, multi-center study where they looked at a lot of CineMR short axis images that were annotated, and they learned this system to recognize this. And so this paper just came out, and we're very enthusiastic about that. In the paper, they describe also the architecture. I will not go into details, but it's a network that really learns pixel for pixel to classify if the image, the pixel in that image, is part of the background or the endocardium or the epi region in the heart. And this way you can get segmentation. For training, they use different data sets in their paper. So roughly there are 4 different scanners used, and they sort of have 100 patients per group used for the training, where they did annotations, and later for testing to really validate that the algorithm performs well, they use 50 patients per group with different diseases and different scanners, as I mentioned, different field of use, different geometric aspects. So they did a lot of comparisons. I'll just show some of the more clinical sort of comparisons where so they looked at the volumes, of course, of the ED at the ED phase and the ES phase of the left ventricle. And you can see very good correlations, and the Blunt-Altman plots as well show that there's a nice correspondence between the fully automatically detected by this network that they trained and manual annotations of the experts. Similar for the ejection fraction, so of course the output of the and the mass of the left ventricle, very nice correlations and comparative numbers with the manual annotations. Some pictures from the paper as well, but David is going to show you the real life cases of actually the data that was not used in this paper to train or to test it on. So these are other data sets that David will demonstrate later, but very nice results on different scanners, different types of acquisitions, and different diseases. Another one here as well, on some Philips and some GE or Seamans data as well. But the live case examples will be much more impressive to show with moving images as well. So we have now integrated it in our upcoming Medis Suite release. We'll be using what's called the outerCue service. It's a processing service that runs either on your local machine, but it can run on a remote machine as well. And especially if you have good hardware, good CPU processing available, then that can speed up the algorithm quite a lot. But the way it started is that it will be launched, it will run in the background, and when it's finished, it will present itself as a new entry in the repository of, in the patient browser. And this new entry you can drag into the existing MAS software and you get the contours available. So that's my part of the webinar talk, and I'll give the word to David to do a live demonstration.
All right, thanks. So I would like to show you how this is going to be implemented now in a Medis Suite workflow. And I've 15 cases here. Let's see how far we can get. And this, the idea is that we launch this this month. So in a couple of weeks from now, that it is available in a maintenance release. The way it works currently is that you can select a short axis series from this browser. And then from here, you can run the outerCue algorithm. So let me just show you what happens. So I can launch here the outerCue for the deep learning contour detection. And it's possible also to queue this. So it will take a little bit of time to run, depending on whether you're running it on the CPU or on the GPU. We will not support officially the GPU, but if it can run, yeah, we can enable it if your graphics card is suitable for it. I have it running on the NVIDIA GPU on my laptop, so it happened to run. And I can show you here, this is for instance a Siemens case with all these cines, and I can also run this one, and maybe I can do a third one just to show you that it's possible to queue this. And yeah, when it's done, you will have this outerCue file that was now generated just now, and yeah, the next one will be running, and this way you can, if you have a lot of cases that you need to process, you could run them first, and then you can go through the results to check the contours, and if needed, to still manually edit them. But let me show you some results. I have here this short axis stack, and I have an outerCue file, so I can load them both into the Medis Suite workflow. You can also load the whole study, but for now I'm just loading the short axis cine. And basically you can just select both from the series browser on the left and load them into QMass to check the contours. So basically that's it. And then here we can see a volume curve. Here we can see the contours, but let me just show you, give the opportunity to take a look. So I'm going to maybe zoom a little bit more. So the nice thing about the algorithm is that it also automatically excludes slices at the apex and at the base, above the base and below the apex. So that is also quite nice. And if you do not agree with a contour, you can still edit, of course, as you're used to in QMass. This is a case where particularly, yeah, I hope you appreciate it. It runs quite nicely for the endo and epi contours. But sometimes if it would be a case that it doesn't run that well, or you're just not interested in a complete volume curve, we also have the workflow where using the shift key, you can drag the contour file onto QMass, and it will only detect the end systolic contours. So for instance, if you do not agree with this, you could just edit it, or you can just exclude it. And then over here we have the end diastolic phase, and then basically in this case we're done, and we have ejection fraction of around 53%. So this is just one example, and of course you can still edit if you would like to do that. So this was a GE case. Now maybe I show you a Seamans case. Maybe this one is nice to show. This was courtesy of Dr. Bull at the Royal Bournemouth Hospital. And I can select both the files here and load it into QMass. So this is an Avanto Fit. This was not a scanner we trained on. It was trained on Avanto, but not on Avanto Fit. And here you have an example of how it looks like. Maybe if I show you the movie, it will be better to see all the contours. So here again, it automatically excludes at the base and apex. Now got a couple of more. Maybe a Philips case is nice to show. This is from Semmelweis University in Budapest. And let me load this case of acute myocarditis. This was actually scanned post contrast. If you watch carefully, you can see some enhancement here already subepicardially. So I can load this into QMass. And then again, we have here the results. So this was an Achieva, Philips Achieva. And here again, at the apex and at the base, it excludes. Now we have at the base, it can be quite challenging. So maybe here the contours you do not agree. So we have this X shortcut to exclude this image. And actually you could select with Shift multiple ones and you can exclude them very quickly. So we have a couple of shortcuts in place that can make it a lot easier to trace. At the apex, it can also be challenging So, but in this case, maybe not too bad. And here in the mid layer, it looks good. And then we get, yeah, volume curves like these, and the mass contour is also quite stable. But again, if you're only interested in ED and ES phase for for routine workflow, you can use the Shift key and drag it in here. Maybe I need to exclude this one again. And then you have the contours in place. All right. So it has been trained exclusively on adults. So will it work for pediatrics or congenital? It may not yet work that well on that. We are in the process of trying to make it suitable for pediatrics as well. We're looking into that, if we can use the algorithm. I have here a case of a tetralogy of Fallot. I think there's a question. So there's a question from Ott Bakermans. Is there some kind of constraint for the ED mass and the ES mass? Well, not that we are aware of that there's a constraint. Maybe I noticed indeed that the difference in the mass is quite small, but it might be a coincidence. Maybe in some other cases it will be a bit larger, but we can see how it goes. So this is a tetralogy of Fallot case, or a pediatric case, and just to give you an idea how it looks like. So at the apex, it has a little bit harder time, and I can show you how it would be possible to edit this actually using our time continuous contour detection algorithm. This is something that not everybody will know how it exactly works. So it's nice to show. This has already been in the software for quite some time. These blue buttons here, if you ever wondered what they're for, I'll show you. So for instance, there are a lot of outliers here. What I can do is turn this on, and then you get this clock. And then when you edit a contour, it will automatically propagate the contour to neighboring slices. And what you typically find is if you do 2 or maybe 3 edits, that the contours are pretty much in place. So I can do a bit contours, and there will be it semi-automatically edits neighboring slices. So that might be nice in case you are interested in doing the full cycle. And again, if you're not interested in that, then just use the Shift key, and you only get the ED and ES contours, and you might need to edit only in those phases. So let me turn this off, and then you can edit here. And the apex can be a little bit challenging, but I believe already in this case, it would be quite saving a lot of time instead of editing everything manually.
There's another question for
yeah.
you. Does it work for the right ventricle?
Not yet. So this algorithm is dedicated for the left ventricle, and this is our first deep learning based algorithm. So we are very excited about results, and we want to further enhance it to work on more types of cases, also pediatrics. And at the same time, we are in the process of training for the right ventricle as well, collecting data sets and export contours, so that in the future it will work for that as well. So that was the question. And then, yeah, we have to see how good we can get it for the right ventricle. And it will work for the ED and ES, but also we would try to do it for all the phases.
There's another question from the same person. What would be the advantage of quantifying the whole heart circle instead of only end-diastolic and end-systolic frames?
The advantage would be that you could also look at diastolic function parameters, like peak ejection rate, peak filling rate, or maybe more advanced parameters if you take derivatives of the volume curve. So diastolic function. So I think clinically today, it's typically ED and ES phases. And so that's probably what you would then want to do. But of course, if it works for the whole face, it's nice to demonstrate. So that's why I'm trying to show you how it works. This is a post-contrast Seamans. So here you can see the result, and maybe at the apex there would be a little bit of editing, but overall it should be pretty decent. And you can see also some contrast here in the lateral wall, indicate there was an infarct, and there actually was also an old infarct here at this insertion point. I think there's another question.
Yes. Does it work with QStrain as well?
Yes, it does. Although this is a test version, so let's see if it works today, because we haven't released it yet, but I can show you that you can launch into QStrain and yeah, pick some slices. It will compute a little bit, something like this. It will compute a little bit longer because we're doing now endo and epicardial contours. But basically, you can then load them into QStrain and do some yeah, advanced wall deformation analysis on the short axis contours. I think in the future, when we also have something for the long axis, then we could also do that. So, and we're also in the process of automating it more. So right now in the browser, you need to manually launch it, the outerCue detection, by right-clicking here. But we are working on also automating that when it comes into the server, that you don't have to do it anymore, and basically it just runs, and then you start with the outerCue file, loading it, and yeah, there's a lot of steps we can do to improve the or enhance further the workflow. So here's QStrain that is running now using those contours.
There's another question.
Yeah.
Can you please show the 3D rendering of the contours?
Sure. Yeah, let me show the next case. I have here a case. This is from one of the face-offs that is being held at SCMR or at EuroCMR, or maybe in Leipzig. And I looked at the data to see how it detects. And yeah, also this case, pretty nice. This is so from a Philips Intera. And I can actually add a reference point. Maybe you don't notice, but if you do that and you go to a 3D, we can start this movie. And this is how it looks like. But actually, we can also in QMass look at, for instance, the wall motion, and then you have a nice idea of yeah, some color coding to it. There's also a feature when you add this reference point, and you can do this. So yeah, this is how it looks like, or maybe you can look at the wall thickening. So that's how it looks like in a movie. I can show you again also in another case. Yeah, about the constraint, I really don't know if there's one, but they are remarkably close. I have seen some cases where they're a bit more off as well, but I think if the detection works quite nicely, then probably they're close. So here's another case. Also, let me see. Also Seamans. No, this is a Seamans. So here the AD and ES mass are a bit more off. So it's not always perfect, and you still always will have to know what you're doing. You cannot totally rely on the computer, of course, and you will need to make some corrections. So here you have an example of, for some reason, it didn't detect perfectly. As mentioned, it has been trained on several scanners, and it's a first algorithm, so we will try to improve this in the future where we can. Also, when you are going to get this version, we would very much like to hear from you how it works, and yeah, we might be interested to collect some new data in case there's outliers, or for certain cases where the training was not optimal. that we can see if we can further improve this algorithm. We can continue to learn. I think that's the beauty of the deep learning, that we can add cases. What I did here is I edited one contour, and with the time continuous detection, I can fix this problem. So let me just show you again here on this other slice. The epi is already fixed a lot, and maybe the endo, or you can also still use this live contour, for instance, option that you might be familiar with. And that will also help speed up, get the contours approximately the right place. But yeah, in case, again, you don't want to look at all the phases, you can use the shift key and drag in, and then you can correct all the contours maybe in the ED and ES. I think for a clinical workflow, that might be just the fastest to do. Oh, I had this one turned on. I need to turn it off. Fortunately, we have the undo here.
Might be good to mention that it doesn't replace the existing detection in mass. It's a pre-processing step, like it shows you drag it in. So if you're used to the traditional QMass detection and you like that, you can still use that. This just adds new functionality to it. It doesn't replace.
This is a nice case from GE. This is a very hypertrophic heart. Might be difficult to detect. So nice to show you this one. And the volume curve is quite nice. Let me show you the contours. So this is the result on this hypertrophic case, where does a pretty nice, I think a pretty nice job.
There's another question. Do you have any example with poor EF around 20%?
I do. I have one, I think. Or I don't know if it's around 20, but I think this one was also poor. Something like this. Yeah. So yeah, actually this is 17%. So it might not be really perfect, as you can see here, but let's say we would do a clinical workflow and you're interested in the ED and ES, then you can modify contours in ED and ES to make them correct. So you would do a little bit more edits here, but everything in red was automatically detected, and everything in orange is then manually edited. But I think maybe you still need to do some editing, and you need to be careful. It's always you decide how the contours really should be in the end, but it should be time saving, and already the first detection is already a lot better than was often than with our more old currently available algorithms. So it should be quite time saving, and this was around 16-17%. Maybe I have another interesting case here, and then I think we're already over time. I can show you maybe this one. I think that was nice. It was also from Hungary. There was some wall motion abnormalities here, I think. Well, let me just show you the result here. So all the cases that we just show you, the algorithm was not trained on any of these data sets. So I think they did a fantastic job in Leiden University to select the right cases, different pathologies, different vendors, to already for adults get very good results. I know in pediatrics it might not work at all. I didn't show you any examples, but we are looking into also making it available for smaller hearts, and the work definitely isn't stopped here. I think we just started with automating expensive tasks. So I think that's maybe we should keep it for this. We show you a lot of examples. Then if you want to see it for yourself, I think we are going to be at RSNA. We're going to be at Euro Echo in Milan. And yeah, if you would like to bring some of your own cases, we can take a look together to see how it performs live. And yeah, then you can maybe get a real impression of how it could work on some of your cases. And again, when we install the version in our maintenance the coming time, then yeah, we also would like to hear very much back from you. How is the performance? Because we can only make it better by following up on cases where it didn't work that nicely. And yeah.
Yeah, maybe also one more thing I would like to mention. There will be a QStrain webinar also coming up on the 19th of November at 2 o'clock. That will be on our website this week, and you also might get an email from us, so you can register for that one as well. So that also can be quite interesting.
Yeah, thanks. There was another question from Dr. Rajinovic from Glasgow. So some information about GPUs and whether it supports batch operations. It does not support batch operations now, but what I did the other day, for instance, with my GPU, I was able to process 45 cases in about 25 minutes. And I just had to manually select the 45 cases. So that took me around 5 or 10 minutes to do so. And then, yeah, doing some other stuff, the cases were processed. I'm using a NVIDIA card, and I had to in order to enable it, it requires some files that we can provide to make it run. And you might need to update a driver version from the NVIDIA. We will not officially support it, but we can always try to help you make it work and share what we know. And I think in the future we will want to support it more, but we need to know a little bit better which cards can and which cards cannot support it. And so we have to be a bit careful not to promise too much that it will always work. So if it doesn't work with the GPU, the cases that I show you that take like 45 seconds on my laptop, something like that, they might take 2 minutes or 3 minutes on the CPU. And that's my laptop. So it can depend, of course, on the hardware. And I think we're running tests at the office, and we have very beefy GPUs, and it will run faster. But yeah, I think there's a lot to further enhance in the future.
Yeah. Okay. So if you have any other questions, you can just contact us, and we're happy to answer then your questions. And it would be nice to meet you at the next conferences or in the next webinar here. Thank you very much for your time, and have a good day.
Thank you. Bye-bye.
Bye.